Welcome to this course, Thermography Camera Fundamentals AHMTT. In this course, you will learn the following contents: Thermal Imaging and Thermography, Thermography Fundamentals, Emission and Reflection, Hands-on exercise. The first part is thermal imaging and thermography. Let the sunlight go through a prism. Rainbow would show up at the other end. This is refraction of light. The sunlight contains light radiation of different wavelengths, including infrared radiation. The prism can refract all of them due to their different refractive indexes. Infrared rays, also known as IR, are always accompanied by thermal energy. There are two types of application based on IR detection technology: thermal imaging and thermography. The first one is thermal imaging. This is non-radiometric. Observation and video content analysis are the important applications. Detectors and cameras are designed to visualize the thermal radiation of objects over a scenery, typically in a grayscale with white as high radiation and black as low radiation. Most common applications are security and surveillance, such as intrusion prevention and handheld observation. The second is thermography. This is full radiometric. Test and measurement are the major concerns. Detectors and cameras are designed and calibrated for test and measurement. Cameras display absolute temperatures with usual accuracy of ±2 degrees Celsius or 2%. The accuracy depends on camera type. For example, temperature screening cameras should be an accuracy of ±0.5 degrees Celsius. This type of cameras can work for both qualitative and quantitative diagnosis. The most common applications are electrical building and industrial inspection. Science and R&D applications can also use thermography cameras. Other common applications are conditions, process, fire prevention and detection, etc. Let's have a look at their typical applications. The thermal detector in the camera can sense the radiation difference in the field of view. Therefore, a thermal camera can both image at a specific moment and continuously image for a long-term observation. This is about thermal imaging. Further, in some security camera models, if a line is in the thermal image, video analysis can perform. The camera can alarm when line crossing happens. As we mentioned previously, thermal energy accompanies IR. When the thermal detector senses the radiation, it knows the surface temperature of an object with a predefined formula inside the camera. In this way, temperature measurement can work. This is about thermography. We'll introduce thermography fundamentals in the second part. This part may be a little tedious. Terms in this section are not important, but keep these images in your mind, please. First, what is temperature? Temperature is a physical quantity that expresses hot and cold. The most common scales are the Celsius scale, the Fahrenheit scale, and the Kelvin scale. Denotes are in these forms. The Kelvin scale is mostly used for scientific purposes. A term, absolute 0 degree, is 0 Kelvin. It is the lowest theoretical temperature. A body of 0 Kelvin means no thermal radiation to the outside. Experimentally, it can only be approached very closely, but not reached. Never ever. 0 K equals -273.15 degrees Celsius. All objects above it have to emit parts of the heat as thermal radiation in IR spectrum. Thermal camera can detect this energy and create an image based on radiation differences. Heat transfer generally has three methods: conduction, convection, and radiation. Conduction usually occurs in solid state. Thermal conductivity is the property of a material to conduct heat from one end to another. Energy can also transfer from one object to another when they are in physical contact. Convection usually occurs in gas state and liquid state. Energy can transfer between an object and its environment thanks to fluid motion. Radiation is a special form of heat transfer and occurs with electromagnetic field. Questions? Question 1. What is the type of this thermal pattern? This is conduction. Question 2. Where is the hottest area and where does the heat dissipate to? The red cross near the center and a connector is the hottest area. The heat went along the cable from the connector near the center to the right side. Let us understand the concepts: heat and temperature. Heat is a transfer of thermal energy and measures how much energy moves or flows. An object can gain heat or lose heat, but it cannot have heat. Heat is a measure of change. Temperature measures how hot or cold an object is. Temperature difference drives heat transferring from an object of high temperature to a lower one. For example, when ice of 0 degrees Celsius mixes with water of 0 degrees Celsius, the mixture is still 0 degrees Celsius. Another example is this: after a small ice block of 0 degrees Celsius gains energy of 100 joules, the ice can become a drop of water. What can we see? Visible technology needs a light source to emit radiation. Light source can be the sun, lamps, etc. The light radiates on an object and then it is reflected on its surface. What we see with our naked eyes is actually the reflection. Colors in the visible range result from the reflected wavelength of light. If there is no light source, visible technologies are not able to see anything. That means total darkness. Let's have a look at the electromagnetic spectrum. Visible light and thermal energy are both in the electromagnetic spectrum, but they have different wavelength ranges. Other typical EM energy forms are X-rays, ultraviolet, microwaves, and radio waves. The visible light ranges from 400 nanometers to 700 nanometers. You may see the range from 380 nanometers to 750 nanometers somewhere else, depending on the reference source. In general, that means a very narrow range. Our spectrum has a wider range in the EM spectrum. High micro uncooled cameras take the advantages of LWIR, short for long wavelength infrared. In the IR spectrum, there are several ranges with high transmittance in the air. We call them atmospheric windows. The blue areas represents the transmittance along the wavelength axis. High micro thermal cameras are mostly uncooled cameras. This type of camera works with LWIR detection technology. You might have seen the spectral range of 7.5 to 14 micron in a micro thermal camera datasheets. Our spectrum typical has four ranges. Technologies vary in the ranges due to the different principles of physics. Near-infrared technology is based on the wavelength of 0.75 to 1 micron. It is usually used in security applications. Short wavelength infrared is based on the wavelength of 1 to 3 micron. The usable wavelength is 1 to 2.5 micron. It is used in R&D and scientific thermography. Mid-wavelength infrared is based on the wavelength of 3 micron to 8 micron. The usable wavelength is 3 to 5 micron. Long-range imaging is the most advantage due to the highest transmittance in our spectrum. Expensive cooled detectors take the advantage of this technology. Long-wavelength infrared is based on the wavelength of 8 to 15 micron. The usable wavelength is 7.5 to 14 micron. Uncooled infrared detector is a cost-effective solution in security and safety and thermography. What is thermography? The term consists of thermo and graphy. Thermo generally means heat and graphy means image. Thermography camera creates an image out of heat radiation. In other words, the camera can draw with heat. Let's have a look at two forms of energy. Sample number 1. The stove is very hot. Temperature is more than 130 degrees Celsius. The heating tube is red, which means the tube also emits visible light energy. Expect thermal energy. Sample number 2. The heating tube beside the red one is not so hot. It emits thermal infrared energy only. A question: are hot objects visible to thermal detectors? For a plate of evenly distributed temperature, what does it look like in thermal detectors? Thermal detectors sense temperature difference. When there is no temperature difference, the infrared image does not show any contrast. This is a thermogram. When a thermal image includes a temperature scale, a thermogram contains the heat radiation information and shows the differences in heat radiation from a scene. Without the temperature scale, a thermal image can only show apparent temperatures in pseudo-color. The shown radiation and calculated temperatures depend on emissivity, measurement distance, reflected temperature, and some other measurement parameters. The first three parameters can be set by in-camera, the others are not usually configurable. Let's see the third part, emission and reflection. What can the thermography camera see? The left picture shows a cup with two tapes on it, and the two tapes are in different materials. Thanks to thermal conduction, the two tapes are isothermal, meaning they are in the same temperature, however, they are in different pseudo-colors. The cause is on emissivity and reflectivity. They produce the contrast. Let's see the relationship between emission and reflection. Emission of heat originates from the material itself. Reflection is a result from what is placed in front. When the energy strikes on an object, it is separated to three parts: transmission, absorption, and reflection. For a cup, the transmission is zero. When the energy of the cup is fully exchanged with the environment, the system is stable. Then, the absorbed energy would totally emit. That means absorption equals to emission. Therefore, the energy in a stable object is the sum of emission and reflection from the stable object. The reflection is actually the surrounded energy reflected by the object. We can see emission and reflection are complementary. That is to say, a good emitter cannot be a good reflector, and vice versa. Emissivity. The capacity of a surface to emit heat is called emissivity, denoted by the Greek letter epsilon. It is a normalized value and varies between 0 and 1, which means 0 to 100% emission. Thermal and electrical insulators are excellent emitters. They have high emissivities. Typical materials are wood, rubber, human skins, etc. Metals are good reflectors but poor emitters. Unless heavily oxidized, their emissivities are mostly 0.25. Typical materials are copper, steel, iron, aluminum, etc. You can use emissivity tables in the user manual. You can also search on the internet. In the nature, nothing is able to emit 100% of energy. An emissivity of 1 is just a theoretical value. In physical world, the theoretical object is called black body. An object of emissivity of 0 is called white body. Everything else should be in between and is called gray body. Please note, a black body source like this in the slide can be used for thermography calibration. This is a device to simulate the theoretical black body. It has an extremely high emissivity surface. Its emissivity can be very close to 1 after energy compensation. Some models can simulate as the ideal black body. Reflections are always present in thermography work. What is a reflection and what is a real high-temperature spot? From the previous introduction, you may understand the importance that we have to know the answers. Let's pause for 10 seconds. Please try to tell where reflections are in the thermal image. Reflection and emission depend on surface material, temperature of object, surface roughness, surface patterns, cavities, grooves, degree of oxidation, and the viewing angle, too. Reflected temperature is an important parameter inside the camera to give a reflection a temperature value for calculating the real temperature. Now you have known the importance of reflection. The viewing angle determines the reflection direction. A right position and viewing angle can make a good thermogram. Do not forget safety, please. The best angle to an object is 45-50. If you found some hot spots and you are not sure if it is a reflection, just change the viewing angle or position. A reflection will disappear or move in the process while a real hot spot remains there. After learning these theories, you can try with the camera in your hands. In this part, we encourage you to follow safety regulations while demonstrating with electrical equipment. The first rule is safety. Please always follow the safety regulations for the location you work. If someone wants to open a switchgear for you, always say no. It is very dangerous to open a medium voltage or high voltage switchgear when it is live if there is any partial discharge presence and any oxygen introduction from the opening, the switchgear will cause an explosion. If you have to demonstrate on a switchgear, do it at low voltage electrical panel, but never ever open it by yourself. PP is usually required in a factory. While doing demo, please do not touch any cables inside. Take off your rings, watches, and other sharp pieces from your arm. Practice safety. There is a demo example, a standard home electrical cabinet with fuses for other rooms. You can see switches in the cabinet. Be careful of emissivity. It may cheat on your thermography camera when reading temperatures. Plastics and cable isolators usually have high emissivity. Metal usually has a low emissivity. Is it a hot spot? Or just a reflection on a low emissivity material? Move the thermography camera. It turns out just a reflection from the inspector's body at a metal surface. The bright areas in the image become darker after change the viewing angle. So, is this an anomaly? Nothing is abnormal in this electric cabinet. There is only one higher temperature area, but still uncritical in temperature. 70 degrees Celsius is a typical critical temperature. At this temperature, isolation materials start to melt and can create a fire. Fortunately, the bright area in the image is lower than 30 degrees Celsius. In this course, we have introduced thermal imaging and thermography in Part 1. The two features are used for different applications. In Part 2, thermography fundamentals and many physics terms are introduced. Those terms are used to explain advantages and limitations decided by some thermography principles. In Part 3, we specifically introduced emission and reflection. The two phenomena can dramatically affect the thermography works. We gave out a solid method to avoid reflection, that is changing the viewing angle. In the last and the fourth part, we emphasized safety during demo and working process. We took a simple example to understand how thermography camera works with a home standard electric cabinet. Thank you for your time with us. Taking the chance you know a lot today. Please go to start the quiz and earn your credits.